Okay, so as a continuation of where we stopped, so we were saying, well, which of the orbitals are quantum mechanically, or rather is quantum mechanically allowed? So we had said that on shell number 5, it is possible to have, on shell number 5, it is possible to have a d orbital, so meaning that a 5d orbital is allowed. Then, however, on shell number 2, it's not possible to have a d orbital. So because of that, this is not allowed. The 2d orbital is not quantum mechanically obtainable. And then on shell number 1 also, you cannot have a p orbital. So this is quantum mechanically disallowed. And then on shell 3, we cannot have an f orbital. And then that is quantum mechanically disallowed. So all of these ones are not allowed quantum mechanically. All right. Then also we can have a situation where you are asked to calculate the number of unpaired electrons. One of the questions that can arise from these atomic orbitals and then electronic configuration is to estimate the number of unpaired electrons. So let us see 2 questions, the number of unpaired electron in ion. Okay, now to get the number of unpaired electron for any atom at all, what you first must do is to write the configuration. So that is a 1s2, a 2s2, a 2p6, a 3s2, a 3p6, a 4s2, and then of course a 3d6. Okay, so we have 3d6. So now what you do to get the number of unpaired electron, you can observe that all of these orbitals are filled. All of these orbitals are filled. They are complete. So this is the only orbital that is not filled, and this is where possibly the unpaired electron will be. So what you do is to try to draw out this orbital. Okay, so this is a d orbital first of all. So d orbital will have 5 degenerate orbitals. Okay, so what we'll do is to place these 6 electrons into these orbitals, and then we are going to have 1, 2, 3, 4, and then 5. And then the 6th one now will come here according to Hund's rule of maximum multiplicity. When electrons enter degenerate orbitals, then the electrons must enter singly first before pairing is possible. So looking at this, you are going to observe that there are 4 unpaired electrons here. So there are 4 unpaired electrons. So 4 electrons are unpaired here. Okay, so you can see there are 4 unpaired electrons here. Okay, then again, if we are to also answer the question, you can also be given to do for ions. Okay, be it anion or a cation. You can also be given to do for ions. So for example, the nickel ion, nickel 2+ ion. Now, if you are technical enough, you are going to observe that nickel, okay, the atomic number of nickel is 28. And the atomic number of nickel being 28, if you have a 2+ ion, if nickel is to form 2+ ion, what it simply means is that it has lost 2 electrons. Remember, okay, so you form positive ions by loss of electron, and you form negative ions by gain of electron. So for nickel to have nickel 2+, it simply means that 2 electrons have been lost, and then it simply means that the number, okay, this, remember, nickel atom will have 28 electrons and then 28 protons. Okay, protons positive and then electrons negative. So to have formed nickel 2+, it simply means 2 electrons have been lost from here, meaning that what it has now are 26 electrons and still maintaining the number of protons there because the nucleus is conserved. So there are 26 electrons in nickel 2+ ion. Now, do you need me to tell you that this is still going to have this same configuration? Okay, it is still going to have the same configuration as ion. And if it has the same configuration as ion, it will simply mean that there will also be 4 unpaired electrons. okay, because the number of electrons here will also be 26. And if you write the configuration, it will be exactly the same thing as that of ion, and then that will result to you having this number of unpaired electrons. So take note of instances where you're expected to calculate the number of unpaired electrons. Okay, now moving on, I can ask you a question, okay? If I'm to test you, then to test your understanding of this topic, then I can ask you a question, okay? Say an orbital has, if an orbital has n value equal to 4 and has L value equal to 2, okay? What is this orbital? What is this orbital? This is simple knowledge. If you remember, we said, before now, we had said that L is equal to 0, okay? And then if L is equal to 0, then that is an s orbital. If L is equal to 1, that is a p orbital. If L is equal to 2, then a d orbital, and if L is equal to 3, that's an f orbital. So if that is so, then that means that L being equal to 2 will simply be pointing to a d orbital. So this simply is a d orbital. This is a d orbital. And then N being equal to 4 will simply mean, if you remember from where we started, N being equal to 4 simply mean that this particular orbital is the d orbital of shell number 4, and that is what that means. So this N being equal to 4 means that this orbital is found on the 4th shell, okay, on the 4th shell of the atom talked about. So this is on the 4th shell. So this orbital talked about, okay, referred to using N equal to 4 and L equal to 2 must be the 4d orbital. Okay, it must be the 4d orbital that we find here. So each of these orbitals will have N equal to 4, and then the L value of this is 0. So N equal to 4, L equal to 0, that is a 4s orbital referred to. N equal to 4, L equal to 1, that is a 4p orbital referred to, and just that way. Okay, so you can be given the principal quantum number and then the angular momentum quantum number, and you are expected to say the orbital in question, okay, or to give the orbital in question, as the case may be for the question that is asked. Okay, and then a few other things now will still revolve around the rules. Okay, the rules will still revolve around the rules, and then, you know, referring to electronic configuration. There are rules, remember. Now, the rules of configuration, I did not talk about it now. We have the off-balls rule, okay, the off-ball, okay, off-balls rule. Then, of course, you know about the Hund's, okay, the Hund's rule, okay. So, off-balls rule. Then we have the Hund's rule. Then, of course, we have the Pauli's principle. Okay, the Pauli's principle or rule. Okay, now what does each one, how does each one apply to configuration? Now this one already we had explained some of them while we were doing while we are on this initially. Okay, so for example, if you remember, we said that these are the order of the orbitals. Okay, 1s, 2s, 2p in increasing energy. So this will simply mean that the 2s orbital is greater in energy than the 1s orbital, 2p is greater in energy than the 2s, 3s is greater in energy than the 2p, and then onwards like that. So if you remember also, we also said during filling that orbitals of lower energy will fill before orbitals of higher energy. For example, the 2s orbital will get filled before the 2p orbital. And then the 3s orbital, of course, will get filled after the 2p orbital is filled. So what that will simply mean is that the orbitals are filled in order of increasing energy. Okay, so from ones of lower energy to ones of higher energy. Okay, and that is what the off-balls principle is all about. Then Hund is saying, if we have orbitals of equal energy, that is orbitals that are concerned with degeneracy, then in placing the electrons within orbitals, then electrons must enter orbitals singly first. then before pairing is possible. Let us do a configuration. If, for example, we do configuration for oxygen. Okay, we do a configuration for oxygen. Now, oxygen would be 1s2, then 2s2, and then 2p4. Okay, so if we are to show how these electrons are fixed in their orbitals, then our interest mostly will be, okay, so this will be the s orbital carrying these 2 electrons. We'll have the p orbital carrying the 2 electrons, and then we'll have this other p orbital, and then there are 4 electrons here. Now, this orbital is 3. Okay, there are 3 orbitals in p, so py, px, and then pz. Now, 4 electrons are to enter into these orbitals. Now, according to Hund, we must not enter these electrons this way. Okay, so 1, 2, 3, 4. These electrons must not be entered this way. Rather, Hund says for degenerate orbitals like this, electrons must enter singly first. Okay, so 1, 2, 3, and then before pairing is possible. Okay, so you must fill the electrons, you must fill the orbitals singly first, then after which it is now possible to pair, after which you can now pair. Then Pauli says no 2 electrons within an atom will have all the 4 quantum numbers the same. Okay, and that is very, very clear. If we use helium with 2 electrons, we are going to observe something. Helium, if you write the configuration, a very simple one, 1s2. Now, you're going to observe that these 2 electrons of helium, okay, now, if you demonstrate the 2 electrons, we're going to have these 2 electrons of helium. You're going to observe that if you illustrate all the quantum numbers, remember the quantum numbers are principal, n, okay, the principal quantum number. Then we have L, okay, which is the azimuthal quantum number or the angular momentum quantum number. Then we have M, which is the magnetic, okay, magnetic quantum number. And then we have MS, okay, which is the spin quantum number, So if these 2 electrons, if we are to write out their quantum numbers, you're going to observe that the both of them, because they are on the same shell, then they will share exactly the same principal quantum number, okay, because they are on the same shell. Now, because they are also on the same orbital, they are going to share the same azimuthal quantum number, okay, and the azimuthal quantum number for S value is 0, okay, then the LO value is 0, okay, for S orbital. Then, of course, M, the magnetic quantum number, is usually illustrated as plus or minus the LO value, okay? In other words, demonstrating one value, okay? There's just only one value for M, okay? Just one value for M. And it is given by whatever the LO value is, okay? So whatever the LO value is, plus or minus the LO value, that will give the M. So you observe that they have all these 3 quantum numbers the same. Of course, they share the same orbital, okay, these 2 electrons. However, you observe that the 4th quantum number, which is MOS, which is the spin, will be different, okay? The spin will be different. And one is going to have a positive spin, and then the other will have a negative spin, okay? So the spin is to show that they do not, go in the same direction, okay, as you can see here, okay? So one has a positive spin, and then the other has a negative spin. And that is what Pauli was simply trying to say. So Pauli is saying that any 2 electrons within an atom will not have all 4 quantum numbers the same. And that is very illustrative, as we have shown in this particular example that we ascertained. Okay, so having said all of this, I think we have done a little justice to this, and then in our subsequent videos we shall take more questions. Thank you.